Hi folks, this is an introduction to the related rates problems that have similar triangles in them. And they're a very traditional related rates problem. I guess you would call it a classic problem. And so what we want to do is make sure we understand the context and do some simple calculations to look at the rates and see if we can understand the relationships. These are ones that until recently I hadn't given a lot of thought about them, but there's a lot to these questions, and it does require a bit of a physics analysis, which we're going to do. So anyway, here's what we've got. We've got a skateboarder here. We have a lamp up here, a light up here, and a lamp post. You can imagine that if it's in the evening, there's going to be a shadow created. As the light comes down, it's going to be blocked out by the person that's skateboarding. So what you see in dark black is the length of the shadow. So that shadow is lengthening as the skateboarder moves along because the angle is changing. And the information that we know is that the skateboarder is 6 feet tall. We know that that lamp is 15 feet tall. And we know that the skateboarder is skating at a constant speed of 3 feet per second. So let's take all this information and put it into a diagram and start doing some analysis. So what we're going to do is take some snapshots in time of this skateboarder. So what I did is I looked at that simulation and then I did basically a screen capture of it every second from 3 seconds until 5 seconds. And that's going to help us understand some things that are happening. So what I did is I called A the bottom of the pole. That's where the skateboarder starts from. And I called the location B right here, and that location is where the start of the skateboarder shadow is, and C is the end of the shadow. So that means that the distance from B here to C here is the length of the shadow. Okay, so if we look at this, A is always at 0 feet, right? A is at 0 feet, and in this case, B is at 9 feet, and C is at 15 feet. So that's at 3 seconds. Then we go to 4 seconds. So where is everyone at 4 seconds? Well, still the pole is still, the lamppost is 15 feet tall. The skateboarder is still 6 feet tall. Of course, that's not changing. What has changed though is they traveled 1 more second from 3 seconds to 4 seconds. So they've gone 3 more feet because the skateboarder is going at 3 feet per second. And now the end of the shadow is 20. Okay, so that means the length of the shadow is actually 8, right? It goes from 12 at B to 20 at C. So the shadow has a length of 8. At 5 seconds, and it makes sense, B is at 15 because 3 feet per second times 5 seconds is 15 feet. But we also notice that in terms of our measurements that the length of the shadow extends out to 25. Okay, the length of the shadow extends out to 25. So overall, the length of the shadow is now from 15 here to 25 here, or 10. So let's look at a summary of all this information in a table of values. Okay, so we've got a table of values here of all the information that we gathered. So at 3 seconds, this is right at the skateboarder. Okay, so he or she was 9 feet, had traveled 9 feet. The tip of the shadow was 15, and so that makes, so the distance from the start of the shadow to the end of the shadow is 15, so the overall length of the, that should say the length of the shadow, not the board. Sorry folks, I'll just quickly change that. That's not the length of the board, that's the length of the shadow. So there's a length of the shadow. And then what we see is at 4 seconds, 12, 20, and then it's 8 long. The shadow's 8 long. And then 5 seconds, the border was at 15. The tip of the shadow was 25, and the length of the shadow is now 10. Let's take a look and see if we can figure out some velocities. How fast are things moving? Well, it was given in the question that the skateboarder was traveling at 3 feet per second. Is that true? Well, at 3 seconds, they had gone 9. At 4, 12, and at 5:15. So I'm in 1 second intervals, so it's pretty easy to do a difference and see that it changes by 3 feet every second. Now what about the tip of the shadow? Right at the very, very end of the shadow. Well, there it's 5 feet per second, 5 feet per second, 15, 20, 25. And then what about the actual length of the shadow? Well, it goes 6, then 8, then 10. So it's going up by 2 feet per second. So what's the relationship here? So if I go and I look at this, what is the relationship between the velocity from A to B, the velocity from A to C, and the velocity from B to C? And let's support that by looking at a diagram as well. So now we're going to look at this with a picture. And what's interesting about this is we can see very clearly that the length from A to B, so this is exactly where the skateboarder's wheel is, that length from here to here is increasing at 3 feet per second. That was given in the question, but the table, or the observations also told us that. Now what we also notice is, so I want you to think about this. This distance right here is increasing at 3 feet per second. This distance from B to C is increasing at 2 feet per second. So that's the length of the shadow. That's what it's increasing by. So if that's true, how quickly is C moving away from A? Okay, think about that for a second. This is increasing at a rate of 3. This is increasing at a rate of 2. So it only follows then that the overall length from A to C is increasing at a rate of 5 feet per second. Okay, so there's actually 3 rates here. There's the rate of the skateboarder, there's the rate that that shadow is lengthening, and then there's the overall rate, which is really, that's how quickly point C is moving, okay, relative to A. So how quickly is point C moving? And I did have a talk with a friend of mine who's a very bright guy in physics, and I told him I thought it was a relative velocity problem, and but I wanted, just to make sure. So we went through it together, and he's the one that said look at it from an experimental perspective by gathering some data to verify your conclusions. So sure enough, we did a bit of work. I didn't pick nice numbers at first, actually, but in the end, the 3, 4, and 5 seconds worked out quite nicely. So we can see really clearly that the velocity is 3 there, which we were told. The velocity is 2 there, and then the overall velocity, which is the lengthening of AC, is 5. So we add them together. So that's the experimental data. Let's look at this and do it with calculus and see if we get the same results.